everyone. These are the examples from the second half of lesson 6.6 for Algebra 2. Really what we're looking at here is going back to the stuff we've learned about exponential functions and learning now how to use logarithms to solve for values up in the exponent. So taking a look at example 4, it sets us up with information as though we were doing a continuous growth equation, but we're solving for when it will reach 300 million. So let's first just start with the continuous growth formula, which we usually refer to as like the PERT formula. And technically PERT, the P stands for principal, which is like for banking, but we can really just think of it as the initial value. So in this situation, our initial growth or our initial population is 250 million. I'm just going to put this in as 250 and then know that our answer is going to come out in millions. I'm using the E because it says that we're doing continuous growth. We're growing at a rate of 1% per year, so that would be 0.01. And then I'm trying to find the when. So that's the T. I'm trying to find how much time this is going to take. And I want this to come out equaling 300 million. So I'm going to put 300 over here. Okay, so take a minute, let that sink in. Make sure all of those pieces make sense. If not, rewind it and maybe listen again. So up until now, to solve problems like this, we've really done kind of some trial and error, or some, we've done some where we've put this in the calculator and then used our table to kind of estimate what T is, but we've never done anything where we've actually solved for T. And now that we know how to use logarithms, we can. So the first thing I'm going to worry about here is this 250 that's out in front. Really, this is the exponential part of the equation here. And so before I do anything with logs, I need to move that 250. So I'm going to divide by 250. So let's see, 300 divided by 250 is 1.2. So now I have 1.2 equals e to the power of 0.01t. Now from here, this is where we dive into logarithms. And we talked about how anytime there's a variable up in the exponent, we use a logarithm to bring it down. In this case, because I'm working with a value of e here in my base, it's going to make the most sense to do a natural log. So in a lot of these problems, we've been doing common logs because that's what our calculator does for us. Our calculator will also do the natural logs for us, and that's what makes the most sense when you're working with e. So I do that, and then this exponent can slide down in front of that natural log. So now my equation looks something like this. Natural log of 1.2 equals 0.01t times the natural log of e. And the reason I said that it's nice to use a natural log here is this thing, natural log of e, really just cancels out. Essentially it equals 1, but if you're just multiplying by 1, you don't really need the 1 for anything. So now I just have this, natural log of 1.2 equals 0.01t. And then to solve, if I want t by itself, I'm going to divide by 0.01. And so in my calculator, I can do this all in one step. So I can do the natural log of 1.2. I'm going to make sure to close that so that I'm only taking the natural log of 1.2, and then divide by 0.01, and I end up with 18.23. That is my t value. And so just to remind you, t represents time in years. So what we really just found is that it would take 18 years for the population to grow from 250 million to 300 million. Okay, let's try another one. So this is another continuous problem. $650 in investment account earning 2.4% interest compounding continuously. We want the balance to reach $1,000. So really I'm using this same formula again. My initial value is 650. My interest rate is 2.4%, and remember I'm going to slide that decimal point over, so that would really be 0.024. And then my t is what I'm solving for, Okay, because again, I'm being asked how long will this take, so I'm trying to find the time. And I want it to come out to equal 1,000. Okay, this might be a little boring because it's pretty much exactly like example 4 was. I'm going to start by dividing by 650. So 1,000 divided by 650 gives me 1.5, well, we'll say 1.54. So I end up with I guess I'll go a little bit farther. I'll go 538 equals e to the 0.024t. And then I would take that exponent, or sorry, I can't take the exponent down until I take the natural log on each side, which once I'm talking in terms of logarithms, then I'm allowed to bring that exponent down in front. So I can say natural log of 1.538 equals 0.024t times natural log of e. And once again, natural log of e cancels out. So now I can just divide by 0.024. Divide by 0.024. And then this is going in my calculator. So natural log of 1.538, close parentheses, divided by 0.024. And I get 17. Gosh, the answer is even really close to the same. It's 17.94. Remember, that's years would equal t. Okay, these examples down at the bottom don't necessarily work the same way as the other things we've seen in this lesson. These are more just a general review of things from this chapter, but these do come up on your next quiz and possibly even on your test. So I wanted to make sure we took a minute and talked about them. So when I look at that first one, couple of strategies when you're solving equations with logs. If you are in a position where you have logs on one side of an equation and not on the other, okay? Like the logs are already there, not a situation where you're taking a log on each side, but you're given an equation that has logs on one side and not the other. My strategy would be to get those logs combined, and remember we have to think about our rules for combining logs, and then turn it around to exponential form. So in this first one, I'm going to think about how the 4x and the 2 are allowed to combine. Since this is addition of logs, I know I can multiply these two things together. So I can write this as log of 8x equals 3. And then I'm going to take this thing, I know it's a base 10 because there's no base written. I'm going to spin it around to exponential form. So that's going to look like 10 to the third power equals 8x. So 10 to the third power I know is just 1,000 equals 8x. And then I would divide each side by 8. So 1,000 divided by 8, I believe is, 125. So x equals 125 here. So if you've got log of something on one side and no log over on the other side, the easiest way to deal with it is to turn it into exponential form. Now, if this had been a situation where I had logs on both sides of the equations, I would have still taken this same strategy. I would have gotten to the point where I could say log of something just by itself here equals log of something else. But then once you have that scenario, if you've got logs on both sides, then you can set the two pieces equal to each other. So this next one, it says 4 times the natural log of 2x plus 5 equals 12. One way or another, the first thing we have to deal with is that 4, because we want to get this to the point where we just have the natural log, and then we can handle it the same way we did this one. We have two choices for what we could do with the 4. One way is much better than the other. So we could put it back up here as an exponent, right? We know that that 4 could be an exponent on the 2x plus 5. The problem with that is I don't want to actually take this thing to the 4th power. I mean, if you think about that, that's like having to FOIL it out 4 times. We don't want that. So instead of making it an exponent, let's see if we can just get rid of it. And we can, because this is multiplication, we can just divide by 4 on each side. So that's how I would start this one. And then I would write this as 4. Nope, sorry, the 4 is gone now. Just kidding. So this would be natural log of 2x plus 5 now equals 3. So now this setup is very similar to what we had here, right? Where we just had the log of something equals something, log of something equals something. I'm going to take this base, which is e, and I'm going to spin this thing around. And I'm going to write this as e to the power of 3 equals 2x plus 5. And I know this might freak you out a little bit, but we can do this in our calculator. Okay, we have e in our calculator. So I'm going to do e to the power of 3. Okay, so I get 20.086. I'm going to try for the most part to keep this decimal in my calculator though. Equals 2x plus 5. And now I'm just going to solve this like an equation. So I'm going to subtract the 5 on each side. So I'm just going to go minus 5. And so now I have 15.086 equals 2x. And then I'm going to divide by 2. And I end up with 7.54. And that would be my final answer there. Okay, this third one. The third one, there is a shortcut for this one. I mean, there's a very easy trick that once you see me work it all the way through, you're going to go, oh my gosh, that was so easy. I will tell you, I never remember what the trick is, and so I always have to kind of start it the same way. Even though this is e to the power of something crazy, I know that with an x up in the exponent, I somehow need to bring that exponent down into the problem. Okay, and the way I'm going to do that is exactly what I learned in this lesson, is I'm going to take a log on each side. Now in this case, because it's an e, I'm going to use a natural log on each side. Okay, I'm kind of squeezing that in there, and then this thing is an exponent, right? So it's going to come down in front, and so now my problem says this. Gosh, I keep picking up that pen. That does not work. So natural log of 7x that came down from the exponent is now being multiplied by natural log of e. So I brought this thing down in front of that natural log of e right there, equals natural log of 21. Now don't go crazy and start crossing off natural logs all over the place, but we do know that natural log of e cancels out. And so now essentially we have natural log of 7x equals natural log of 21. This is a different situation than what we had here. Up here we had the log just equal to a number on the other side. Here we have a log equal to another log. If these two logs are equal to each other, then these two values must be equal to each other. So this must equal this. Okay? And so then I can say 7x must equal 21. And therefore that means x is equal to 3. So the little shortcut is basically that if you're doing e to the power of a natural log, the e and the natural log kind of cancel themselves out right here, and you're left with just the 7x that was here originally. I know that's kind of a mess for you to see. Like I said, I struggle with remembering that. And so I always kind of just work it through this way. Even if I'm just working it through in my head, I'm always thinking about, all right, I would take a natural log on each side. I would bring the exponent down. And then my natural log of e disappears. And I'm left with two natural logs that are equal to each other, which means the two things that we're taking the natural log of must be equal to each other. And then I can solve the equation from there. So those are some examples that I don't know that you'll necessarily see on your 6-6 homework, but they definitely come up as part of your quiz review, and they will be on your next quiz. So just wanted to make sure you had a chance to see them first. All right, that is it for this lesson. Go ahead and get started on your homework, and As always, you can come see me in class if you have questions.